The number of particles squirted in, this is about 50 particles, is going to be always shown to us in this graph, but not on the axis number of particles, because what we're looking at on this graph, called a Maxwell distribution, is the number of particles and the speed that the particles are moving at. So the area of this graph will always have to represent the number of particles in our sample. In this case, that would be 50. Those areas are going to take on different shapes depending on what's happening to our sample. You'll see that the speed distribution on the left has a lot of the particles kind of moving at a general slower speed. Just like a normal speed graph, slow speed is towards the beginning, and as you move to the right, the speed gets higher. You'll also notice that the graph is not symmetrical. There's a skew off to the right. Let's go ahead and heat the gas. As we heat the gas, you realize that the particles pick up in speed. They have a higher average speed now, around 700. Look at what's happened to the graph. Do you see that the graph has become kind of shorter and longer? Because the number of total particles can't change, that means the area under our graph can't change. So there's two distinct shapes that our graph will take on, a short and fat and a tall and thin. So let's go ahead and ice that system, bring down the temperature. As you do that, you'll see our graph on the left will begin to change. So the area must remain constant, but now more of our particles are moving slower. So our graph takes on this tall shape, and our particles have decreased in velocity. All right, so you just looked at what a Maxwell distribution curve shows you. And here is an example of just a medium temperature sample. And what you see in our sample here is this peak. So this is the most probable speed. That means that you have most molecules moving with that specific speed, most probable. So if you grab 1 out of 100, like most likely it's going to have this speed out of any other speed. That's different than the average speed because the skew is right. So this brings up the average a little bit. So our average is a little bit higher than our most probable. And then that is a little bit different even than the velocity we can calculate using kinetic energy, which is called the root mean squared. So let me remind you of the distributions that you saw in the video before. So compared to this average temperature sample, here is a sample that is not as hot. Notice that these speed markings would all be bumped down to something that is a lower total speed number, right? Closer to 0, 0. And now why, as these numbers get lower, does this peak have to get higher? Well, if the number of total molecules doesn't change, but these numbers on the x-axis go down, the area must remain the same, so that means that we must have a taller distribution. Now let's look at something that is hotter. Right, here's something that is hotter. So when something that's hotter, all those speed numbers would move out to the right, but the peak would drop down because, again, that total area needs to be the same number because it's the same number of molecules in the sample, right? So unless you open the door or latch the lid or squirt in more gas, these areas are all the same, which is why you have to see this shortening of the peak when you increase the temperature, because you're increasing those speed numbers. So the average still has to come out the same. Now, this kind of makes sense because when you're hot, what are molecules in a hot sample doing? They're like bouncing all around. There's way more collisions. There's way more stuff happening, right? So there's going to be a lot more randomization to the motion inside a hot container. Just like if you put people in a room and you made them run around real fast, there's going to be a lot of collisions. Some people are going to be running fast, others are going to be running slow. Some are going to be colliding like pretty often and transferring speed to other people in other ways. Okay, so that's our Maxwell distribution. So just to go through this with you, Maxwell distribution graphs gives the number of particles per unit speed. So the total area under the curve is equal to the total number of molecules. Here's your example of cold room temperature hot gas. So remember, short and fat, that's hot nowadays. So let's go through and look at some questions on page 9. You'll see this has a sample that's the initial and final conditions. We want to know what's the difference about the initial and final stage of the gas. So tell me some facts. Which one's hotter? Which one's colder? Do they have the same number of molecules or not? Is anything the same? Then experimentally, how can you make this happen? All right, so here I'm in my kitchen. I have this container where I'm going to put a fixed number of molecules in it. How can I fix the number of molecules? I'm going to put a lid on it. There are two types of lids that you can have. You can have a lid with some screws, in which case my container can undergo more than just atmospheric pressure, right? So this is a container in which the gas can get really hot and push against the container and it won't just explode out. With my other type of lid here, I can seal it, keep the number of molecules in, it's rubber, but if I don't twist it on, then if the molecules become more than heated up to the point where they're pushing on the lid more than atmospheric pressure, the lid will just pop off. Right? So I'm going to go for the sample where the pressure can change because the volume of my container cannot. The volume is fixed. And in those graphs, you notice the temperature was different. How am I going to make the temperature different? I'm going to use every cook's favorite technique, the microwave. That's done. But want to be careful because it's going to be hot. Here's my hot sample. And if you could see the molecules, they would be moving faster. But you can't. All right, here are the next two questions worked out. Important to notice the conditions of your problem. So you have this sealed container. That means that the N is constant. You can't change how many molecules are in there, which also tells us that the area is going to be constant. Then it says we're going to place it in an ice bath. So we're going to put it in a bucket of cold water, and it's going to decrease the temperature. So bucket of water, temperature goes down. Okay, what is going to happen as the gas cools? The peak height of the graph and the number of molecules gets shorter. No, remember when you're not hot? This is not hot. Okay, so that can't be. The average molecular speed of the gases decreases. Well, that's true, right? The gas speed is going to decrease when the temperature decreases. The graph of the number of molecules versus speed becomes narrower. Narrower. Yep, that's true. Look at that baby compared to the probably sample that it was before, right? I guess the sample that it was before is probably room temperature. Something kind of like this. But certainly not like this. The hottest of the hot. Notice that all of these need to actually start at 0, 0 for making it a graph, which I wasn't originally graphing people. All right, and then the root mean squared, the gas is going to increase. That's not true. As we said, it was going to decrease. Which action could be taken to make this distribution graph? First, let's realize what happens. Here's our first stage. Here's our second stage. Do those areas look the same? No. So that means there's more molecules in here than there is in here. Now, let's think about the speeds of those particles. Here, they're moving at a higher speed, and here, they're moving at a lower speed. What could that mean? Well, remember, speeds are directly related to temperatures. So this is something hot, and this is more like something that's not. So let's figure out which one of those actions. No molecules are allowed to enter or exit. That can't be because the area changes. Some of the gas molecules are allowed to leave. Ooh, that sounds good. And the remaining gas is cooled. That's totally possible. That matches our situation because there's less area and the peak velocity is less. Let's just check the other ones. So this won't work even though they do allow them to leave because the particles are heated. Then this one doesn't work because it says that particles are entering.